Good afternoon. This presentation is about OpenMP. It's a technology that can be used to implement multi-threaded programs. I will use the terms multi-threading, parallel processing and parallel programming interchangeably to mean the same thing as far as this presentation is concerned. Okay. So, some introductory slides. Why is parallel programming required? Computer applications ranging from computer games to sophisticated software used in weather forecasting perform massive repetitious computations, and these computations often have parts that can be executed in parallel. Okay, so also we know that there have been tremendous advances in the capability of hardware. These days even laptops come with multiple processors, so all this raw compute power can be exploited in the software with technologies like OpenMP. It's just one of the technologies that is available for implementing multi-threading, but there are quite a few other technologies available too. Here are some examples where parallel processing could be useful: large simulations, problems in linear algebra, graph traversal, etc. We'll take this first example, large simulations, in this presentation. As a programmer, I have got the opportunity to write software that performs statistical computations, and some of this software also performs simulations of different aspects of clinical trials, and we'll just look at that today. So what is OpenMP? It stands for Open Multiprocessing. It's an open standard for writing programs, portable and scalable programs using languages like C, C++, and Fortran. It is an API. It is an application programmer's interface, and so it is a collection of compiler directives or pragmas, and also library routines and environment variables. And it supports workload division among multiple threads and synchronization and communication between these threads. So let's look at our example, large scale simulation. The simulations that I have worked on typically go through these steps. You perform the initialization, then you generate the data. This step also involves generation of random numbers. Then you analyze that data, and then you summarize and combine your results or aggregate your results and perform some cleanup at the end. This is how the picture would get modified if you use multi-threading. So now the core steps of the simulation are executed in parallel by multiple threads. This red rectangle that you see around the core steps, that indicates a certain kind of loop, like a for loop or a while loop, and as you can see, the iterations of the for loop are being executed in parallel by these three threads. The thread that starts the process is called the master thread, and the other threads are the child threads. Okay. Here is a simplified sample code. This code is written in C, and it's highly simplified. The actual code is much more complicated than this, but I think it serves the purpose today. So I just perform some initialization in the beginning, allocate memory, things like that, and then there is this loop that's going to execute the core steps of the simulation. Notice this interesting line before the for loop, hash pragma OMP parallel for ordered. This is a compiler directive, OpenMP compiler directive, that tells the compiler that when the master thread enters this loop, it should create 0 or more child threads and distribute the iterations of the for loop among these threads. One important thing to notice is that if only one thread was executing this for loop, it would execute the iterations in the sequence. But when multiple threads are executing, the sequence is not guaranteed. So it's possible that the 10th iteration of the loop may start and finish before the 5th iteration. So your logic should not be dependent on the sequence of in which the iterations will execute. So that's one condition. We are now inside the body of the for loop. Here we're generating random numbers. Again, notice the use of another pragma, OMP ordered, and after that I'm generating trial data. We'll talk about OMP ordered a little bit later. And in the final step, I have just crunched everything into this final step, analyzing and summarizing of the data. And again, one more pragma, that is OMP critical. So let's look at a small animation. Here I'm showing a loop that is executing 5 iterations or 5 simulations in our case, and these iterations have been divided among or distributed among 2 threads. So thread 1, which is also the master indicated by the blue arrow here, it's going to execute simulations 1 and 2, and when it enters the for loop, it creates one more child thread, and it executes the remaining iterations 3, 4 and 5. Both threads are essentially executing in the same steps, but they take their own time, and when one thread is done, it has to wait for the other to catch up. At the end, the child threads exit and only the master continues beyond the for loop. Let us now look at the compiler directives or pragmas that we used in this code snippet. First, the OMP parallel for. This is a work sharing directive. It tells the compiler that the workload in your program should be divided among multiple threads. As we saw, the master thread creates the child threads, and there is an implied barrier at the end of the for loop, which means that all threads must wait at this barrier for other threads to finish their work, and only the master thread can continue beyond the barrier. You can modify the behavior of your threads, or how they are created and how the work is shared among them, using some clauses or options that are available with this compiler directive. Yeah, thread synchronization is an important topic whenever you are writing multi-thread programs, because often in your program there are resources that are shared among multiple threads, like there could be a shared memory location or there could be a shared file. You don't want two different threads to access this shared resource at the same time, because the resource could get corrupted and your program could give wrong results, or it could just misbehave. So you have to synchronize. One example is random number generation. In this case, those who have worked with random number generators, they know that it is essentially a sequential process. When you generate one random number, the seed gets modified, and the seed is used to generate the next random number. So a process like this cannot be parallelized. You have to generate random numbers in sequence. So this is perfectly all right. With OpenMP, you could have parts of the program that you don't want to parallelize, and so you could put that pragma OMP parallel, OMP ordered around it to tell the compiler that this particular step should be executed by only one thread at a time, and it should be executed in exactly the same sequence as it would when only one thread performs the entire loop. Okay, so that's about OMP ordered. The next example is summarizing output across simulations. Although the simulations are different, we finally want to aggregate their results into one shared memory object that's going to store your final output. And so you don't want two different threads to update this output object at the same time. So to ensure that, you could use the pragma OMP critical, which ensures that only one thread updates your memory object at one time. Here the sequence does not matter really. So you could using this OMP critical pragma, you could ensure that the memory updation happens in a consistent manner. So whenever a thread reaches the critical block, if some other thread is already executing the code inside the block, it has to wait for that thread to finish. Only then it gets an access to the code inside the critical block. So let us look at some practical results, the improvements that we have got with OpenMP. We have a product called Size, which performs sample size computations and simulations for fixed sample clinical trials. So here are two sample test cases executed with Size. When we ran the test case without OpenMP, you can see that it took 6 minutes 40 seconds. This was a clinical trial with 2,100 sample size, and we performed 85,000 simulations of that study. And with OpenMP, we got an improvement of 69% in terms of speed. In the other case, a clinical trial with the sample size 3,800, and we performed 100,000 simulations of that, and again we got an improvement of about 55% with that when we used OpenMP. So this is quite a substantial improvement in the performance, and this kind of improvement is real, and you can get it by using a technique like OpenMP. OpenMP is not the only technology available. You could do it from first principles by using the Win32 API, but then that needs just a lot of work Of course, you get more power. You can do many more things when you use something like this, but it just needs a lot of rework. You have to redesign your program and all that. Excuse me. MPI is another popular technology. It's more useful for grid programming. OpenMP cannot be used for grid computing. MPI can be used for that. Again, MPI is generally considered more difficult to program, but in some cases there is no alternative. You have to use MPI. So finally, just some concluding remarks. OpenMP is a simple and flexible technology. It's quite powerful, and it is supported on many architectures like Windows and Unix, all the popular architectures. It works on platforms from laptops to supercomputer. But yeah, one has to read and understand these specs carefully and design your software properly. And ultimately, once the coding is done, you have to test it very thoroughly to make sure that the results with and without OpenMP match, and you get what you desire. Some references. The first one is the OpenMP website. You can download the latest specifications from this website. The second is a book. It gives you comprehensive reference to OpenMP. And the examples are in Fortran, but even C++ programmers could use that. The last one, sorry, that's an article from the MSDN website, and it's a very good introduction to OpenMP for the beginners. So that's all for today. Thank you very much.